Welcome, everyone. Uh, to be fair, I actually don't remember which episode of Iron Widow this is, so let's call it the next episode. I guess this might be the last episode of this year, but actually might not be. Well, we'll see if I have enough steam to do one more this year. And yeah, let's get started. Uh, Today we have an interesting topic because we are actually changing topics. Kind of like looking back at the previous episodes, we kind of like handled two arcs already. The first arc was where we discussed super high-level engineering aspects about Tragabido, like why we are building it like from first principles, why we are building it with zero dependencies, why we are solving like a particular problem of like tracking financial transactions. The second arc discussed, well, let's say aspect-oriented aspects of Tragabido's code. We kind of like looked at a very high level at like random source file of Tragabido and that told ourselves, hey, like why is it looked at this way? Like why it is using callbacks? Why it is written in Zig? Why it doesn't allocate memory after startup? And we, I think, like mostly covered that. So today, this episode starts a new arc where we will be looking at our consensus protocol. Like what is consensus, how it works, why we use our particular protocol, how we test it, etc., etc. This is probably going to be like a larger topic than the previous two, but well, we'll start small. And in particular, today we actually are not going yet to touch the consensus itself. Rather, we discuss the topic of replicated log, replicated state machine, and kind of like the overall like semi-physical model of data in Tragabido. So let's get back to our famous white Tragabido document and see what we have here. And we actually, let's like go back to the very first, one of the very first bullet points here that we want to double. Where is double entry counting? Oh, it's not very first, but the top bullet, double entry counting. So the idea of double entry counting is that you like basically have accounts, transactions. There's like some rules about how transactions, in particular transfers, change accounts and how the state of an account evolves. the question is, how would you actually represent this data internally? Because there are like two forks in the road here. You can go with like state-based representation, or you can keep it event-based. When I say the state-based representation, I mean that kind of like we literally model our world as a set of accounts with like certain balances. And when a transfer comes in, we actually go and change balances in place. And this is like world is what we have. For event-based representation, we kind of like keep this account state implicit. In event-based world, let's actually clarify this. So in state-based representation, state is essentially like hash map, account ID, account balances. If you recall in double entry accounting, we actually have separate balances for debits and credits. For event-based system, like the state is going to be just a list of transfers. And the state of account is actually derived by running this list of transfers. And the question is, which representation is better? And probably like your intuition tells you that, hey, kind of like event-based makes more sense because it is like more flexible. The issue with state-based representation is that it fundamentally erases information. Once you have a certain state, you don't know the path you took to reach to the state. While in the events-based representation, you just never erase information. You just append events onto an ordered list of events. And that unlocks like all kinds of interesting possibilities. Like for example, for event-based state representation, you can easily do audits because all the events are there. You can easily do backups because you could just like stream the events themselves, and that is your backup. You could easily do replace, you can like capture some amount of traffic from your production instance, and then you can like replay it on your staging instances every time you do a rolling upgrade. So kind of like in general, like this list-based representation is a nice thing to work with. And like that's why kind of like we use it. It turns out to be kind of like that one of the important properties of this event-based representation is that an atomic change to the model is a single event. And a single event is bounded in size. And that actually will help us quite a lot in consensus algorithm. I don't want to run too far ahead here, but basically kind of the idea of consensus is that you want to like agree on something. And if the thing you want to agree on is the entire state, well, that's like a lot of data to even check that it is the same across different replicas. While atomic events are like much simpler. And if you just order events relative to each other, and that's all you need to agree upon, because the actual state kind of like is derived from all those events. So yeah, events also kind of like, besides like just being operationally simpler, events help you with consensus as well. So that's kind of like the reason why we model state as events. I guess it used to be called event sourcing. And that like, basically goes back to double entry accounting and also reliability. And I guess you could say this. Oh, you could say that this also has like performance and availability because well, events are small, you can stream them, but that's kind of harder to argue things. So let's say it's kind of like this is an issue for our problem. that it's like double entry counting. And also like events, because they have this replay capability, they are actually reliable, because if something goes wrong, you could always roll back your state and just replay the events. So let's look how we could actually use our events. Okay. Hey, why it takes so long to load? Maybe it's actually not right. Okay, because it is common, not .io. That makes sense. Okay, yeah, let's remove all our Z versus Rust rumblings and look at our log of events. So this is like the logical timeline, and inside this logical timeline, we are going to have a bunch of events, like one by one. Let's say do a couple more doubling so that the picture makes reasonable. Yeah, so this is like our timeline. This is like a bunch of transactions. And if you look at this picture, something should ring a bell, because if you recall our like previous couple of episodes, one big idea of Tragibito is that everything is strictly limited. There are no things which grow unboundedly. And with events, it kind of like looks like you want this sequence to grow unboundedly, which is like bad. So what we do here, and like, isn't this really a problem? And this sort of is really a problem, even if you like store like arbitrary number of events and like some hard drive where you don't necessarily have like the storage limitations. Because if your event sequence grows larger, then the time to replay all the events from the beginning grows longer as well. And that is bad, because the way you want to recover after a crash is that you want to replay all those events to get the state. So if your recovery is proportional to the lifetime of your cluster, that's kind of like sad, because that means that if the cluster is old enough, then recovery is basically impossible. It takes longer to recover than like, let me say it more accurately. Like in an old cluster, you might end in like Achilles and tortoise situation, where like while you're recovering, users pile even more events on top of you, and like while you then process after recovering the first batch of events, like that, everything that was piled on top of you, like you also waste time. And I think you will eventually recover as long as your recovery speed exceeds the intake speed. But well, it still kind of like makes for a pretty long recovery. So yeah, that's kind of like that. What can we do here? And one thing we can do here is, yeah, and actually to kind of like make this a little bit more consensus related, it's important to keep in mind that while this is logical timeline, kind of like physically, it's going to exist on several records. So physically, we like look at a picture which is more like this. Okay, so we kind of like established that we want this event source, the sequence of events, because it is operationally more flexible. But we also established we actually don't want to have this infinite sequence of events, because that requires infinite amount of time. Well, not infinite, but unbounded amount of time to recover after a crash. And the idea here is to introduce periodic checkpoints. So while logically we still think about the state of a system as a sequence of events, once in a while, we actually go and create a checkpoint. Like, for example, let's say that we do a checkpoint every 4 events. And checkpoints are not exactly straight, but no. And like every time we do a checkpoint, we actually go and compress the state which we accumulated up to this checkpoint into like a single thing. So if we let's say we are not at an even amount of checkpoints, let's say we are somewhere here, so we like get up to this checkpoint, and then we have just 3 out of 4 messages here. If like a new replica starts up and wants to restart from backup, it doesn't actually need to sync all these events. What it needs to get, just like this checkpoint and these 3 events on top. So we transfer just a limited amount of information to get the new replica started. And that is basically the idea behind replicated state machine. So our logical state is a sequence of events. Our physical state is a checkpoint plus a suffix of events which builds on top of checkpoint. We want to replicate this state machine across multiple replicas. That's why it's called replicated state machine and not just state machine. And for replication, the idea is that you could sync the latest checkpoint and then the suffix of events which builds on top of checkpoints rather than the entire history. So let's take a look how this actually is implemented in Tiger. Well, of course, everything is bound. And if everything is bounded, a natural thing to do is to say that, hey, actually, I'm not going to have like this whole like virtual infinite log in our memory. Rather, we compute how many events in memory do we need to keep. And a simple answer here would be that, well, we need exactly 1 checkpoint worth of the events. So our physical state, actually, to show that it's physical, can I show that this is, yeah, with rectangular edges? Yeah, we could say that, hey, this is our physical state, just a fixed buffer. Actually, let's maybe do some colors here. So we have like, okay. I'm wondering like, yeah, okay, basically, let's get with color. So this is like 1, this is 2, 3, I should not press Shift, 4, 5, 6. Okay, so this is our like logical sequence of events, and when we try to move it to our like physical sequence of events, what we will do is that we will, okay, let's move it like the whole thing. We'll do a ring buffer situation basically. So we fill 1 wrap of a log, and then we actually go and start overriding those entries. Now, overriding the old one. So this one is gone, and this one comes on top of it. And then with this one is gone, and then this one comes on top of it. So yeah, you would imagine that this is how this works in Rust Analyzer, but reality is still slightly more complicated, because if you recall, one thing we like to do in did I just say Rust Analyzer? I need to remember that I'm no longer working on Rust Analyzer. It's like Iron, so it's in Iron, it's like Taggable. Yeah, one thing we really like to do in Taggable is biting things up. And well, let me just like right now kind of like this hand wave this away, because to explain this we need to dive deeper into log structures merge tree and compaction code, which I don't want to do right now. But basically, if you look at this picture, there's like this problem that once you hit this checkpoint boundary, you have to compress quite a bit of operations at the same time, and like move them on disk and say, hey, this is a checkpoint. So we don't actually want to do this, because that will be like this is spike. And what we do rather is that I actually want this to remain blue. But I want to introduce a concept of checkpoint. And I want that one to remain blue as well. I want a new one. Yeah. What we rather do is that we introduce a concept of so-called checkpoint triggers. So although physically the checkpoint happens here, well, logically, the checkpoint happens at the blue bar, we only get to compression. Actually, let's color code this in a better way. Okay, so I want all those things to have, yep. And then all these things are going to get yellow, and then this one would be yellow as well, and then this one is going to be green, and then this one is going to be green as well. Yeah, so you see, this is our log, and we only get physical checkpoint on disk for these 4 events once we hit this checkpoint trigger, which is slightly ahead of our logical checkpoint. So it turns out that the physical situation on disk is like slightly more complicated. We have space in our log for a checkpoint, and a little bit more for this so-called checkpoint trigger. And if you look at the data on disk, so it looks roughly like this. So we like filled data for checkpoint. Then we started writing events for the next checkpoint. And once we hit the end of the log, we actually, okay, I need to move these somewhere. Yeah. Once we move to the end of the log, once we hit this trigger, we actually go and checkpoint all those things. After the checkpoint, we will start overriding previous entries. And then once we override a whole checkpoint worth of things, we will do a next checkpoint. And you see what happens here. So due to this extra slack, the point in this ring buffer where we do our checkpoint actually kind of like floats. So the first checkpoint is right at the end of the ring buffer, but for the next checkpoint, it's going to be here. And for the next one, it is going to be here, and so on and so forth. So this is how this logical idea that we have events and periodic checkpoints is manifested inside Tagevital in its log of fixed capacity. So let's stop drawing pretty pictures and actually go and look into the code how this all works. Okay, so the important data structure here is checkpoint, which is just a manifestation of a couple of functions which determine various relationships between which events are checkpoints, which events trigger a previous checkpoint, and this. So all events are numbered, and this U64, which is passed as a parameter, is a number of events. And for example, the trigger for checkpoint takes an event which is assumed to be a checkpoint. So the event, the iteration number at which checkpoint logically happens. And then we go forward from this event to the place where we actually know that the checkpoint is on disk. And this is mysteriously named constant LSM dash multiple, which is also the worst named constant in RRRReplicated. But we'll get to this later. Right now, treat it opaquely. Just realize that hey, there's checkpoint, there's trigger, and the trigger is slightly ahead of a checkpoint. Okay. And then so this kind of one operation for a checkpoint, we can get a trigger. Alternatively, for a checkpoint, we can get a next checkpoint. And the next checkpoint is going to be ahead exactly by the length of the checkpoint, which is a constant called SR checkpoint interval. Okay, so in a sense, this describes the logical sequence of events when checkpoint and triggers happens. The physical side of the things, the actual ring buffer, is situated in this journal.zip, and this is what we are going to look at for the rest of this episode. So in this journal, we have a bunch of slots, and let me find slot count. Okay, where are we actually using this slot count? Yeah. So here we allocate parts of our journal, and this is going to be the backend memory for our ring buffer. And as you see here, we allocate we allocate exactly this slot count thing, which is separate from this logical checkpoint, but is related with this picture. And actually, to make this slightly more realistic, let me note that the way we define checkpoint interval is slightly more nuanced. So there is our physical size, the physical number of slots. We subtract from it this magical LSM batch multiple constant, which I explained is needed to slightly postpone the time when we get a checkpoint to avoid latency spike. And then we subtract one more thing, which is more directly related to the consensus, which again, I'm not going to, okay, let me explain this in a way which doesn't make sense, but then come back to it later once I explain the consensus. So the idea here is that while certain events are committed, like we know that they are indeed parts of a canonical log, they are like their own truth, certain events are in flight. So our log has to accommodate not only things which we know are part of the canonical sequence of events, but also things which are speculated, things which could become part of the log of events, but might also not become a part of this canonical log. And the problem here is that when you add those speculated things, they can actually start kind of like, let's say, like you want to add this. Okay, let's actually draw this speculative event as like transparent. When you start to actually add this speculative event, it displaces this oldest event from the log. And this might be slightly problematic because in consensus protocol, to ensure that the D2 is available, you always want to hold many copies of the data. And you are only allowed to remove an event from log of events once you get a guarantee that there is enough of copies of a checkpoint elsewhere, which might not be the case if you don't actually add this extra slack to the checkpoint interval. So that's kind of like this, the purpose of this extra term here, to make sure that once we start erasing old entries from our ring buffer, we get a guarantee that either entry exists either on a quorum of replicas or on a quorum of checkpoints. But again, this is like the precise relationship between the journal slot count and the checkpoint interval isn't actually like that important. It's like the only thing important to keep in mind is that those are actually different. There is like a physical amount of slots in our ring buffer, and then there is the logical amount of iterations across which we do checkpoints. Okay, so what's in the log? What's is in this like journal.z, which is like the write-ahead log. And so the purpose of this thing is to store incoming iterations. And again, because we want to ensure durability, it's not enough to just store all those operations in memory. So this thing, this journal, actually goes and writes all those events on disk. And the ring buffer I've been talking about is actually, well, a ring buffer that exists on disk. And actually, let's just like go and look how it works. So let's start from the right path, the iteration which adds a new event, and you prepare to this ring buffer, and that's going to happen in write prepare. So yeah, what this should do is that it should take this message, yeah, this message, this one, figure out the position in the ring buffer where this message should go and write it there. So let's look how it works. Okay, so this position is called slog. And if we look at how it is implemented, okay, actually, I think write prepare might be not the first thing we are doing here. Yes, because we like this thing writes prepare, but before we actually go and write it, we actually assert that we have a corresponding header. So let's roll back a little bit to the replica and see how we actually get here to kind of like, again, if you don't understand something in the code, usually a good way out is to take a step back, but not back, but like above to find out how the code which calls our thing works. And well, this is the call to append in our replica, and Okay, and here we also actually kind of like check that we already have this in the journal. Okay, let's take a step back once again. Let's go to the onPrepare call, which accepts the message. Right. Yeah. So this is what I was looking for. So the first thing we do is that we actually go and register that we want to append a new prepare on disk. So before we go and write anything on disk, we actually take the header of this prepare, which is basically the header of the message, with the most important thing being the checksum of the entire message. And we go and we write this in memory and say that, hey, this slot on disk is now actually dirty. So at this point in time, we want to have a prepare which corresponds to this header to be on disk, but it isn't yet there. We are asynchronously writing it. And this is actually something kind of like interesting high level aspect to it. And then again, that this is how concurrency looks. This is like real concurrency. So although like everything is like single thread, and you don't even like know that, hey, we don't even like have a callbacks here, because well, we like want to write the prepare on this. This operation takes time. We will tell our operating system, hey, dear operating system, please write this 1 megabyte of a message to this in this particular file in this particular offset, and it will take time for the operating system to do this and return to us back when maybe many other things happened. But when we do this, there is a logical moment in our program when we say, hey, from this point on, we are writing the prepare on disk. And it doesn't really matter whether we've already issued a syscall to go and write this prepare. What matters is that like internally in the logic of our program, we like track this as, hey, this is happening. And this is the place where this is the place where this logical write of a message happens when we register that, hey, actually in journal at this slot, and let's see how slot for header is defined. It should be defined relatively simple. So we have a header, we extract from this the op, and I don't think I think this is the right place to cover it. So op is sequence number of an event. In this replicated log, all events are numbered from 0 to infinity. And this number trivially defines the slot in this write-ahead block ring buffer. And yeah, this is just trivially. We just take an iteration and divide it model slot count, just kind of from first principles. Again, the slot count is that constant which defines how long our write-ahead block needs to be. Okay, so we to append the prepare to journal, we first register that we actually writing this prepare. Then, well, look how convenient. Look how convenient. So I was looking at like this write prepare, and I was wondering like, hey, here we kind of like assume that we already have a header, so what actually triggers it? But the function which appends the header was just above that, and that's actually good. When you write the source code, it's very good if you lay out the code in terms of like in order how it's going to get executed. So we first call the header as dirty, and then we call write prepare, and that's why those two are consecutive in source file. Okay, so we get the header. Now we actually want to go and write this message. We pick the slot, and here kind of like in the slot for header, we just go and fetch the index corresponding to the iteration of the header. In slot with header, we additionally check that the header we have in that slot actually is the same header that we wanted there to be. So that iteration is the same and the checksum is the same. Because again, this is a ring buffer, so many prepares are going to many headers are going to inhabit this same slot over time, and we must additionally check that hey, this is really the one that we want to have there. Then we check whether we actually okay, let's look at these two things. Yeah, we actually check whether this slot is marked as dirty, and when we append a header, we actually do mark this slot as dirty, because dirty is a bit set of things which where the state on disk doesn't yet match the state on memory. And if it turns out that actually this slot is already clean, for example, the way we get to this write prepare is from the concurrent prepare, then we don't have to do anything, and we actually can invoke callback right here. And this is actually bad. Like this is like bad because there is like this like golden rule of asynchronous APIs with callbacks that if your callback-based API takes a callback, it either always invokes the callback synchronously, or it never invokes callback synchronously. Here, it turns out that we will invoke callback synchronously if the prepare is already in the journal, but otherwise we are going to like invoke it once we do this write. So this is not good. What you really want to do here is to like on the next event loop tick do this, or even better, at the call side you could like push this if up at the call side, so that the call side is aware when it can complete synchronously and when it needs to be asynchronous. But okay, anyway, this is like not interesting. The interesting thing is, well, what happens when we actually need to write this prepare on this? And here we're going to see something quite curious. Well, first of all, we're going to see like just boring stuff. First, we like allocate a write for this prepare, and again, everything is bounded. So the journal has a fixed number of concurrent write operations that it can support. Let's see how this is defined. Process journal. Okay, that should be okay. Yes, I didn't find it because there is additional type here, but basically that the journal can write at most 8 to be in journal prepare. So we could write at most 8 prepares at the same time, and if we don't actually have a slot, well, then we say that hey, we like can't write this prepare. And again, this is okay because the code at a high level is like going to retry. And this is actually kind of like, again, one other aspect of the code that we generally assume that things fail. For any iterations, we kind of like do it optimistically. We like try to do it, but it can always fail. And it is okay if anything fails because it eventually is going to be retried. So this is again like one interlocking aspect of a design that hey, you have fixed limits on everything, so you need to like do something while you cannot complete an operation because there is no resource available, because you cannot just like arbitrarily allocate the resource. But it is almost always okay to just return a zero result, return default, to say, hey, I cannot do this at this time. Please try again later. Because elsewhere in our code, we have this control loop that will be retrying this operation until it gets done. So kind of like this is like you have to have both limit on everything, but also a retry loop on top, so that this limit on everything actually doesn't prevent you from completing operations. But anyway, it's again like boring set cases. Let's say we actually had a write. So we fill it. We say that hey, we like want to write this message, and this is again a nice thing. Let's recall. So you hear that you see that we like store a message, and we increment the reference count here. And if we go back to message pool, mess pool. I said to you like, hey, here is like a bunch of increments for this constant for like how many messages do we actually need, and I see that hey, we like right now understand like this part, and other parts we'll understand later. So right here on the right, we are looking at exactly this part, journal IOPS write max, because well, this write comes from journal writes, and we have exactly this amount of writes here. So we kind of think this all is interlocked. Okay. So we fill the data in our write. We prepare a slice of bytes which we want to write. Then we compute the physical offset on the disk where we want to put this data in. And again, let's look at this like offset computation. Offset again, this is like offset on disk. As this is offset on disk, we use U64 here, not a size, because well, disks might actually be larger than RAM, and like usize addresses only things in RAM, not necessarily on disk. And okay, we have like write and prepare, like basically like foreshadowing. It turns out we actually have two ring buffers. We actually have ring buffer with headers and ring buffer with prepares. But right now we're looking at ring buffer with prepares. And here we kind of think, what's the physical offset to write this message to? Well, we know that everything is bounded, so messages are also bounded. So we know that like, each message occupies at most this amount of bytes. But then we just multiply this by index and get an offset in an index. But that's an offset in an index. What? Okay, that's an offset. That's an offset in the ring buffer. We also hopefully will soon see code which converts this to an absolute offset in the data file. Okay, anyway, get like this relative offset. Then we zeroing out extra fighting because, well, this is operation with disk. This is using direct I/O, so everything is done in sectors. Like you cannot write, like disks are block devices. You cannot write a single byte to disk. You always, especially if you do direct I/O, and we are doing direct I/O, and at some point I will probably explain why we do direct I/O and not rely on operating systems page cache. But well, you're here with me for quite a few more episodes. Anyway, everything is done in sectors. So when we want to write a message to disk, we actually don't want to write like just a message. We need to write Actually, yeah, we need to like pod the message to the sector size. So we do this padding here, and then we zero the reminder. And I'm wondering if we could actually just, just assert that message here size percent constant sector size equals 0. Probably not. Probably not, because events like transfers and create accounts are smaller than a sector, and we use size in the header to specify the amount of events we send a single message. So we actually cannot add messages to this, but yeah, that's still an interesting idea. Anyway, we prepare the buffer, and then we say, hey, using this IO resource, we want to write this buffer to this ring of prepares and not headers at this offset. And this write sector hopefully should do log sectors. Why are we doing this log sectors? I think okay, I think log sectors is needed for headers, because actually for prepares, I don't think we could ever have overlapping sectors. But well, anyway, basically, what this thing does is that it prevents concurrent writes to the same region on disk from occurring. I think, again, I don't know this code all that well, but yeah, I guess here is where we actually hit the disk, where we say, hey, like write stuff to storage. And yeah, I think we say that, well, you see, interesting. Interesting, because that's actually, okay, I was thinking that this is the place where we convert this relative offset to an absolute one, but again, this happens like one layer deep. So in storage, in write sectors, okay, in storage, in write sectors, we pass relative offset, but also like the zone in the data file which you're writing to. And the zone isn't like an index, it's just like one of these 6 things. And there is this zone called while prepares. This is a write ahead log, this is journal, and this is like configuration that sometimes in code we use write ahead log, and sometimes we use journal, and they're kind of like synonyms. But also sometimes we kind of like use both of them actually differently. Well, anyway, nothing is perfect. Even targetable is not perfect, but it is like the closest thing to perfect which I know in the realms of software. Well, which I personally work with. I would say that probably SQLite is like closer to perfect at this moment, but we are getting there. We are chasing that. Anyway, so zone is just like some fixed amount of things, and a zone has an offset. Well, and each of those, where are the sizes? Yeah, each of those zones have a size, and a size of all prepares is, as you imagine, just the size of the message multiplied by the size, the number of slots in our journal. So, okay, every zone has a message, so we could compute the start of the zone by just signing the sizes of all the previous zones. And that's why in storage, our write sectors, we can actually convert this relative offset in the zone to an absolute offset in storage, and then go and write data, please. Anyway, we done. Oh, not really. We done with half of it. Because let's unwind. So this is journal. This is writing prepares. And after we write prepare, we invoke a callback. And in a callback, we actually write a different thing. And that's, well, I guess we are almost at an hour. So that's going to be left as a cliffhanger. Uh, and what happens here is, yes, we like do a redundant write. The idea here is that we write a prepare, and then we separately write an extra small record, just the header of this prepare just written, to a different area in our data file. So again, instead of like writing prepare automatically, we actually do this as two operations. And why do we need to do this? And this brushes a little bit on a deep topic, which we're going to dive deeper into at some point. And that is the topic of storage fault. So the thing is with disk is that when you put something to disk, you cannot be sure that it stays there. If you later, like a day later, or a month later, or a year later, come back to this same offset on disk and try to read data out of there, you might actually get garbage, right? The checksum might be mismatching. There might be something else because disks like don't guarantee 100% durability. They guarantee you almost 100% durability, but there is absolutely a non-zero percentage of real disk faults. So when you write something in the journal, when you write prepare on disk, you need to be prepared for the situation when this prepare betroths literally and is not available later. So prepare on disk can get corrupted. And that clashes with consensus algorithms, because consensus algorithms generally assume that, hey, if you write something to disk, it stays there. And kind of like if you try to read something from disk and the checksum mismatched, that we can assume that the thing wasn't actually written there and kind of like go back on some of our consensus commitments. Which again doesn't really match with physical reality of disks because they fail. So kind of like basically what I boil down to is that when you have a replica and you read something from a journal and that something is wrong, like the checksum doesn't match, there might actually be two possibilities here. One possibility is that the thing you're looking for to read was never actually written to disk. This machine never had this prepare, so it can guarantee that it didn't see it and like that fits back in consensus algorithm. Or the second possibility is that the machine actually did have this prepare at some point. It had written data to disk before, but at some point later, the data got corrupted. So again, if you check some mismatches, that means that either the data was there once and got corrupted, or that the data never was there. And for the purpose of consensus algorithm, we actually need to be able to disambiguate between the two and to like say where it's the first case or the other case. And that's why we do this redundant write. That's why we write prepare in one slot, and then separately we write prepares header, so that if we didn't actually write this prepare, then we didn't write both of the header and prepare, and well, we could see this. Whether in a case of a corruption, what we will see is that we will see corrupted prepare but intact header, or intact header, or corrupted header and intact prepare. Anyway, kind of like we can reasonably assume that at least one of those two things would not be corrupted. And that would allow us to conclude that, hey, if one of those things isn't corrupted, that means that at one point we actually had this prepared in memory. And yeah, that's why we cannot guarantee to others that we've never seen this, which is running ahead quite a little bit, because to understand why we need this, we like first need to dive deeper into the consensus, and then we actually need to dive very, very deep into the storage fault model to like fully like understand how all this works. So as I've said, that's going to be left as a cliffhanger. And here, let's recap. So what we've learned today? We learned today that the logical model, which makes sense for like databases, is the model of a log, a model of like a sequence, monotonically increasing sequence of events, which define the physical state at a given point in time as an accumulated effect of all the events up to that point where we do a cutoff. And the reason for that is like events are operationally nice. The problem with events, though, is that when you want to restart, the restart time for replaying events from the very, very beginning is unbounded. So instead, we want to combine those events with the checkpoints. We want to periodically take a snapshot of a state, which is the result of like the first, I don't know, thousands of events, and then write it to disk so that we can truncate our event log up to that point. And during restart, we could only care about transferring this snapshot and the small statics of the log. And then we looked at how we realize this logical model of event log into our physical code in Target code. And the idea here is, well, everything has a limit. So let's say that the amount of slots in our write-ahead block in our journal is limited and is called journal slot count. And then let's figure out how big should our checkpoint interval be so that we can fit everything. And then we could, just write simple code which will go and put data disk where it needs to be. But as we kind of like noticed, the code is not as simple because we also must be aware that the disk can actually fail. But that story is for a different time. The big idea today is replicated signature. And with that, let me say goodbye for maybe a week, maybe a year. I don't know yet where we will have another episode this year, next week, but we'll see. Thanks for joining and watching, and we'll see you relatively soon. In any case, thanks and goodbye.